Ever wondered if there's like a limit to how much order we can impose on infinity? It's a head scratcher, right?
Yeah.
But that's actually what's got me so fascinated by this 1972 paper by Saharon and Shelah.
Yeah.
It tackles this head on in the world of mathematical logic, no less.
Oh, wow.
We've got excerpts to dive into.
Okay.
And what's wild is that it connects combinatorics, how we count and arrange things,
Right.
to the very structure of mathematical theories.
It's truly groundbreaking stuff, and it all builds on the work of the legendary Paul Erdős,
Oh, okay.
a mathematician practically obsessed with these puzzles of how we divide and arrange sets,
Wow.
especially infinite ones.
Okay, so we're already in deep water with infinite sets, but bear with me. One of the key things Shelah tackles is the idea of a strongly cut sequence. It's like, imagine a bookshelf so well organized you instantly know where any new book should go,
Right.
based on what's already there.
That analogy perfectly captures the essence of a strongly cut sequence.
Totally.
It's all about being able to determine the position of an element based on the existing order.
Okay.
And this concept becomes crucial later on when Shelah links it to the stability of a theory.
Okay.
Essentially, how well-behaved a mathematical system is.
Now, I'm no mathematician, but I'm starting to see how this idea of cutting sets in very specific ways matters.
Yeah.
And speaking of cutting, the paper dives into these properties P1, P2, and P3.
Okay.
They're like different rules for how we can make those cuts in a set, but in a mathematical sense.
You see, P1, P2, and P3 provide a framework for analyzing how sets can be divided and organized. And this framework becomes incredibly powerful when we start connecting it to the broader concepts of stability and order in mathematical theories.
So hold on, we're going from organizing bookshelves to the very foundations of mathematics. Things are about to get really interesting. I can feel it. This paper even disproves one of Erdős's own conjectures,
Yeah.
which just shows you how this exploration pushes the boundaries of what we know about order and infinity.
Absolutely. It highlights that even the most brilliant minds can be surprised by the intricacies of these mathematical concepts.
Wow.
And one concept that really caught my eye is this idea of dead, short for Dedekind.
Dead. Sounds ominous, like some ancient mathematical spirit guarding the secrets of infinity. Laughs. Well, it's not quite that dramatic.
Okay.
But it is profound. Imagine trying to pack an infinite number of desks into a hotel with infinite rooms.
Okay.
Dead gives us a way to talk about the limits of how efficiently you can do that, how densely you can pack things into an ordered set.
Okay, now that does sound like something straight out of a mind-bending math puzzle book.
It is.
Wow.
And it's not just theoretical. Think about designing a database.
Okay.
If you know there are inherent limits to how much you can pre-organize infinite data, you design differently.
Right.
Shelah's work, through this idea of Dedekind cuts, hints at those design principles.
Now, this is where I love how seemingly abstract math connects back to the real world.
Yeah.
So we've got strongly cut sequences, these P properties for cutting up sets, and even dead messing with our hotel reservations.
How does it all link to this big idea of stability in mathematics?
That's precisely where we're headed next.
Okay.
And it's where the paper takes a truly fascinating turn. By exploring these seemingly disparate concepts, Shelah builds a bridge between combinatorics and model theory, the study of the logic and structure of mathematical systems.
Right.
And that bridge is what allows us to explore the limits of order in entirely new ways.
All right, so we've got our cutting tools and a sense that even infinity has its organizational limits.
Yeah.
But how does this all connect to the bigger picture of like stable and unstable theories?
Okay.
I have to admit those terms sound a little intimidating.
Think of it this way. A stable theory.
Okay.
It's like a well-designed machine,
Yeah.
right? It behaves predictably.
Okay.
Even when you scale it up to a massive size. Unstable theories, on the other hand, are more like that chaotic system we were talking about earlier.
Right.
Full of surprises.
So our well-organized bookshelf versus the room full of monkeys and books.
Exactly.
Okay.
And what Shelah does is connect those seemingly simple ideas of like cutting and arranging
Right.
to the very heart of what makes a mathematical theory stable or unstable.
Now that's what I call thinking outside the box. Or maybe inside the infinite sets. But how do we actually find those points of instability in a mathematical theory? It's not like we can just look for the monkeys wreaking havoc. Right?
Right. It's much more subtle than that.
Right.
And this brings us to one of the paper's most important results, Theorem 2.5.
Okay.
This theorem is remarkable because it actually gives us a tool to pinpoint those sources of instability.
Wait, hold on. We're not just talking about describing chaos anymore. We're talking about having a way to actually analyze and dissect it. That's huge.
It is huge. Imagine trying to understand a complex network.
Okay.
Like the interconnectedness of the internet. Theorem 2.5 gives us a way to find those critical points.
Wow.
Those links that, if broken, could lead to cascading failures.
So instead of just knowing that a system can be chaotic, we have a way to understand why and how it becomes chaotic.
Exactly.
It's like having an X-ray vision for mathematical structures.
And that's not an exaggeration. What Shelah achieves with this theorem is a deeper understanding of the limits of order.
Okay.
He's saying that even in the pristine world of mathematics, there are inherent limitations to how much structure we can impose.
I'm starting to see why this paper is considered groundbreaking.
Yeah.
But you mentioned the internet just now. Are you saying that these mathematical ideas about stability and order have implications beyond abstract theories?
Absolutely. And that's what makes Shelah's work so fascinating.
Okay.
While he's working within the realm of mathematical logic,
Yeah.
the concepts he's grappling with, order, chaos, predictability, these are fundamental to how we understand the world around us.
So we've gone from organizing bookshelves to mapping the internet, all thanks to this idea of stability and mathematical theories.
Yeah, it really is remarkable.
It's mind-blowing to think that these abstract concepts have such far-reaching implications.
What's remarkable is that Shelah isn't just providing answers. He's giving us a new set of questions to ask about the world. If even the most rigorously defined mathematical systems have these inherent limits to order,
Right.
what does that say about our attempts to understand something as complex as the universe?
Yeah.
Or even just our daily lives?
It almost makes you want to ask, can we ever truly know anything with absolute certainty if there's always this potential for instability lurking beneath the surface?
That's a profound question.
Yeah.
And it gets to the heart of what makes Shelah's work so thought-provoking.
Okay.
He's pushing us to confront the limits of our own understanding.
Right.
Not just in mathematics,
Yeah.
but in every field of knowledge.
And perhaps even more importantly, it encourages us to be comfortable with that uncertainty instead of striving for absolute order.
Right.
Maybe it's about learning to navigate the space between stability and instability, between what we can predict and what will always surprise us.
I think that's a wonderful way to put it.
Yeah.
Shelah's work isn't about shutting down exploration.
Right.
It's about opening up new avenues of inquiry.
Okay.
It's about recognizing that the pursuit of knowledge is an ongoing process.
Right.
One that's constantly evolving as we encounter new challenges and new forms of complexity.
So where does this leave us, our intrepid listener who has bravely ventured into the world of infinite sets and unstable theories?
Hopefully with a sense of wonder and a thirst for more. This deep dive has only scratched the surface of Shelah's contributions to mathematical logic.
Right.
But I hope it has sparked a curiosity about the hidden structures that underpin our understanding of the world.
And who knows, maybe the next time you're wrestling with a chaotic situation, whether it's a messy desk or a complex project, you'll find yourself thinking about strongly cut sequences or the limits of depth. There's a certain comfort in knowing that even mathematicians grapple with the balance between order and chaos.
And if nothing else, perhaps this deep dive has provided a new appreciation for the elegance and power of mathematical thinking.
Yeah.
After all, it's through these abstract explorations that we often stumble upon the most profound insights about ourselves and the universe we inhabit.
Well said. And on that note, we'll leave you to ponder the mysteries of infinity and the ever-shifting boundaries between order and chaos. Thank you for joining us on this deep dive, and remember, there's always more to explore.